Welcome to my integer optimization course. I am Professor Alberto Del Pia from the University of Wisconsin-Madison, and this course is based on the excellent book Integer Programming by Conforti, Cornuéjols, and Zambelli. In chapter 1, we're going to see three different sections. In the first one, we introduce integer programming and some of its special cases. Then we introduce the two main algorithmic principles that are currently used to solve integer programming problems. And these are branch and bound and cutting plane techniques. Finally, in section 1.4, we recall the concept of convex hull and we discuss perfect formulations. Let's then start with section 1.1, where we introduce integer programming problems. We start with the definition of pure integer linear programs. A pure integer linear program is an optimization problem of this type. We want to maximize a linear function cx subject to a number of linear constraints ax less than or equal to b. Then we have the constraints x greater than or equal to 0 and x integral. Now let's try to understand this pure integer linear program a little bit better. The data, so what is given to us, consists of the vector c, the matrix A, and the vector b. Our goal is to find a vector of variables x such that ax is less than or equal to b, x is greater than or equal to 0, all the components of x are integer numbers, and among all these vectors x, we want to find one that maximizes the linear function cx. Generally, we will denote by n the number of components of our vector of variables x. Accordingly, the vector c will then be a row vector with n entries. The matrix A will need to have then n columns, and we generally assume that it has m rows. And this means that we're looking here at m linear inequalities. Of course, the vector B then must have m entries. Throughout this course, we always assume that the data is rational, so that the vector C, the matrix A, and the vector B all have rational entries. In some of the theorems that we're going to prove, this rationality assumption is fundamental, and the same statement just wouldn't go through with more general data, like for example real data. Now, the set of points x that satisfy ax less than or equal to b, x greater than or equal to 0, and integral is called the feasible region of this pure integer linear program. And it is also called a pure integer linear set. So by definition, a pure integer linear set is a set S containing points in Zn plus, so non-negative points in Zn, such that Ax less than or equal to b. In the picture here, we have an example of a pure integer linear set. This set consists of all these black dots here. In this case, n is equal to 2. As you can see, all these points lie in the positive orthant, and we're looking at, let's say, three linear inequalities. One would be the inequality corresponding to this line. The second one would be an inequality corresponding to this line over here. And the third one, an inequality corresponding to this line over here. In particular, note that this set is infinite, because going in this direction, we will have infinitely many points in this set. Next, we define a mixed integer linear program, in short, MILP. This is the program that we will study for most of our course, and so in short, we're gonna call it also simply integer program. Here, the notation looks much more complicated, but really the only difference with respect to the pure integer linear program that we just saw is that we are allowing to have two different types of variables, those that are required to be integral and those that instead can be simply continuous. If we denote by x the integral variables and by y the continuous variables, then our mixed integer linear program takes the form maximize cx plus hy subject to ax plus gy less than or equal to b, x greater than or equal to 0 and integral, and y greater than or equal to 0. The data in this integer program consists of the vectors c, h, the matrices A, G, and the vector b. if we assume that x has n components and y has p components, then A must have n columns and G must have p columns. The number of rows of A, G, and the number of entries of B must coincide, and like in the pure integer case, we let this number be m, so that we have exactly m linear inequalities encoded here. Once again, we will assume that all data is rational. The feasible region of a mixed integer linear program is called a mixed integer linear set. So a mixed integer linear set is a set S defined as a set of points xy in Zn plus times Rp plus, subject to Ax plus Gy less than or equal to b. We have an example in this picture. Again, this is dimension 2. In this case, we have n equal to 1 and p equal to 1. So the x variable is constrained to be integer, while the y variable can be continuous. We have the requirement that x is greater than or equal to 0 and y is greater than or equal to 0, and the three additional linear inequalities given by these lines. The first one over here, the second over here, and the third over here. Now the set S is the union of these vertical black segments. And, like the previous example, also this mixed integer linear set is infinite. So far, we have seen pure integer linear programs and the corresponding pure integer linear sets. And then we have seen mixed integer linear programs and mixed integer linear sets. There are other important classes of integer programs, all of which are special cases of mixed integer linear programs. One case is when all variables are binary. In this case, we have a 0-1 linear program, and the corresponding feasible region is a 0-1 linear set. Then we have the case of both binary and continuous variables. The corresponding optimization problem is then called a mixed 0-1 linear program, and its feasible region is called a mixed 0-1 linear set. Finally, we have the very special case where all variables are continuous. This is technically not an integer program, because in an integer program we require to have at least one integer variables. Anyway, this optimization problem is called a linear program, and the corresponding feasible region is called a linear set or a polyhedron. The only key difference between linear programming and mixed integer linear programming lies in the presence of the integrality constraints. So a natural idea is to take a mixed integer linear program and the corresponding feasible region and just throw away these integrality constraints. In this way, we should be back to some more familiar setting. So, given a mixed integer linear set defined as before, we introduce its natural linear relaxation, which is exactly the same set, but where we replace Zn plus with Rn plus. Correspondingly, if we look at the mixed integer linear program max cx plus hy with xy in S, we define its natural linear programming relaxation to be the linear program where the feasible region S is replaced by the feasible region P0, which is a polyhedron. In this slide, by throwing away the integrality constraints, we transform the mixed integer linear program into a linear program. So a natural question is, what happens if we solve, instead of the mixed integer linear program, the linear program that we just obtained? Let's look at an example in dimension 2. In this example, we maximize 5.5x1 plus 2.1x2, subject to two linear inequality constraints, non-negativity constraints, and integrality on both variables. On the right, we see a picture of this feasible region. We have the two linear inequality constraints, which are these two, plus we have the two non-negativity constraints that also are linear inequality constraints, of course, and they give us these two inequalities. And so the feasible points are all the integer points contained in this quadrilateral. This is a very small integer program with only 8 feasible solutions, and by enumeration you can check that an optimal solution is the vector 1, 3. And its objective value is 11.8. Now we can look at the natural LP relaxation. This is a linear program with the same objective function, the same constraints, except that we drop the integrality restrictions. The feasible region of this linear program is precisely this quadrilateral defined by our 4 linear inequality constraints. If you solve this linear program, you will see that the unique optimal solution is given by this vertex, which is 1.3, 3.3, and the objective value is 14.08. Based on this simple example, one might wonder if we can simply pick our optimal solution to the linear programming problem, round it, and obtain an optimal solution to the integer program. In the example that we have just seen, this is correct. We rounded the optimal solution of the natural LP relaxation and obtained an optimal solution of the original mixed integer linear program. However, in general, this is absolutely not true. In fact, there are 2 main problems. The first one is that even rounding to a feasible integer solution can be difficult or impossible. And secondly, even if we could do that, the feasible solution that we find can be very far from being optimal. In fact, the optimal solution to the natural LP relaxation and the optimal solution to the original mixed integer linear program can be very far away. As an exercise for you, I ask you to come up with some nice examples where this can happen. So it seems that this idea of solving the natural LP relaxation of an integer program might not be so smart after all. However, it really is at the basis of the most successful techniques that are currently known to solve integer programs. As you can expect, these techniques are more advanced than that. And to discuss them, we will need to consider more general linear programming relaxations. Given a mixed integer linear set S, we say that P' is a linear relaxation of S if P' is a set described by linear inequality constraints only, and that contains the set S. Then, if we look at an integer program with feasible region S, a linear programming relaxation of this integer program is simply obtained by replacing the feasible region S with the polyhedron P'. The natural linear relaxation is then a special case of the linear relaxation, where the system of linear inequalities is precisely the one that defines the original set S. Similarly, the natural LP relaxation is a special case of a LP relaxation, where the feasible region is the natural linear relaxation of the original set S. Now the question is, why do we look at linear programming relaxations? There are 2 key reasons. The first one is that we can solve linear programming relaxation efficiently in theory and in practice. From a theoretical point of view, we have algorithms like the ellipsoid method and interior point methods that can solve linear programming problems in polynomial time. From a practical perspective, we have algorithms like the simplex method and interior point methods that can solve linear programs with millions of variables in just few seconds. However, even if we can solve a linear programming relaxation efficiently, this doesn't mean that they can be useful for integer programs. However, we will see that it is possible to generate a sequence of linear relaxations of a mixed integer linear set that provide increasingly tighter approximations of the set, and this will help tremendously in solving the integer program. This concludes our first video, and in the next video we will enter into some more details about these LP relaxations, and we will see the 2 main techniques that are used in practice to solve linear programs.